Okay, so hello everyone. First of all, thanks to the JuliaCon organizers and also thanks to the organizers of the symposium. My name is Jorge A. Pérez-Hernández. I'm a flight dynamics engineer working at the European Space Operations Center. I work there as a contractor for Telespazio Germany, and what we are going to present here is an ongoing work in collaboration with Luis Eduardo Ramírez Montoya, who is a Master of Science student in Mexico National Autonomous University, and also with my former PhD advisor, also at the Mexico National Autonomous University, Luis Benet. And we are presenting propagation of large orbital uncertainty sets with TaylorIntegration.jl. So as a refresher on Taylor's method, the core of Taylor's method is just to start with an initial condition and then compute recursively the Taylor coefficients and then approximate the solution in time as the Taylor expansion of the initial condition in time. And in order to do this, we use some recursion relations, and which using TaylorSeries.jl we can compute automatically. And using them, then we can compute the solution in time straightforward. Okay, and in Taylor integration, we have a control for the step size, for the time step size. And what we just ask the method is just to have a control on the last two terms of the Taylor expansion, and we ask them to be smaller than a certain error tolerance. Okay, and then building on top of that, we have implemented in Taylor integration a technique known as jet transport, which in some other scenarios is also called differential algebras. But jet transport is just essentially a numerical technique which allows to compute, to approximate the solution around the small neighborhood of the nominal initial condition as a Taylor expansion both in time and also on the perturbations. And this is an alternative to using Monte Carlo iterations, which sometimes can be really computationally expensive to do. And yeah, using jet transport is together with the Taylor method is essentially equivalent to solving the qth order Taylor expansion of the solution around the initial condition x0, or you can also see it as solving the qth order variational equation, and we get all the derivatives with respect to time and with respect to the initial condition automatically using Taylor series and Taylor integration. Okay, and one of the main drawbacks of using jet transport to propagate small neighborhoods around the small neighborhoods around the nominal initial condition is that we have the method has no control over how big the neighborhood is. So the longer you go in time, then the convergence radius of your neighborhood shrinks. And the longer you go in time, the smaller the neighborhood is. And then it comes to a point where it is, in order to preserve accuracy for a fixed sized neighborhood, then it becomes easier to start to propagate other nominal initial conditions. And in a sense, if you have a large domain, then you can start splitting that domain and propagating small initial conditions certain on those small domains. Okay, and so, but Luis Eduardo is going to talk about that with more detail. So as an example, we have the Kepler problem with some initial conditions, and we propagate them for 6 periods, right? And in our setup, we have, we just put using Taylor integration, we declare the equations of motion. And then in order to use jet transport, we just have to set these variables. This function is coming from Taylor series, right? And then the initial condition Q0 is just Q00, which is the nominal or reference initial condition, and this other part in the initial condition are the perturbations, right? And then these are only the integration parameters, and then we call TaylorInteg, which is the function we use to solve ODEs in the Taylor integration setup. Okay, and in this example, we have on the left panel an integration with Monte Carlo, and on the right panel we have naive jet transport. And as you can see, as time goes on, a small uncertainty starts to spread out due to Keplerian shear, essentially, right? And if we let this thing run for many more periods, then we would get to a point where the orbital uncertainty starts to spread out over the whole orbit, right? And okay, just for having an example which is more clear, if we propagate an even larger neighborhood, then we start to see things like this, where the jet transport integration starts to drift away from the Monte Carlo reference, right? So this tells us that we have already gotten into a point where the naive jet transport integration is propagating bigger neighborhood than what our error control in jet transport can achieve, right? So, okay, in order to solve this, we have implemented automatic domain splitting, which Luis Eduardo is going to tell you about.
Okay, so as we've seen, a single jet transport polynomial has problems representing the uncertainty when the region of interest is too big. And this can basically be traced back to the coefficients. In the polynomial that we use, the norm of the coefficients can grow for various reasons. The two main factors are truncation errors, which are related to which order we use to expand both in time and in space, but also because of singularities of the differential equation. So in examples like the Kepler problem, these coefficients tend to grow as two bodies approach each other. And to mitigate this phenomenon, in 2015, Wittig and collaborators introduced a technique called automatic domain splitting, or ADS in short. And the idea behind ADS is pretty simple. We start with a domain where we can trust our polynomial, and we propagate it in time. Eventually, the truncation error will accumulate, so if we keep propagating, the polynomial representation will deviate from the actual region of interest. So instead of that, we split the original polynomial into two parts. Each of the new polynomials will represent 1/2 of the original domain, and we can treat each polynomial as a completely independent initial condition, and we can keep propagating each polynomial separately. We can repeat this splitting process every time the truncation error grows too large for a particular tolerance. So we've implemented ADS into Taylor integration, and the code that we would use to study the same Kepler problem is pretty much the same. There are only a few extra parameters. We have to specify the domain that we want to propagate. We also have to specify a tolerance, which is going to define the threshold when to split or not a polynomial. And we can also set a maximum number of splits, because we will see that this technique tends to produce too many splits that can become quite expensive. So here we can see the same problem as before, but the rightmost panel shows the equivalent ADS integration, and the title shows the number of splits at any given time. So while the naive jet transport that uses a single polynomial breaks, the ADS integration remains consistent with the Monte Carlo approach throughout the whole integration. Yeah, I think, okay. Now, ADS is quite sensible to the coordinates that we use to parameterize the perturbations, and that's because the direction of largest uncertainty does not necessarily align with the coordinates that we use. So in this case, the largest uncertainty is along the orbit, and in general, that's not parallel to neither x or y. So a better set of coordinates would be the orbital elements. In this other animation, we again show the time evolution of a uncertainty box, but this time the perturbations are over semi-major axis and eccentricity. So basically, all the splits occur along the semi-major axis, and also there are less splits. As a brief note, the output of an ADS integration naturally resembles a binary tree because at any given time, each polynomial can split at most into two parts. So we've used the abstract trees API to write a custom binary tree named ADS binary node that contains all the information from the integration. And we also have useful functionality like iterating this tree or evaluating it. Now, perhaps one of the most interesting applications that we have in mind for ADS is to study close approaches between the Earth and some asteroid. In particular, Apophis is a very famous asteroid that will approach our planet on April of 2029. In this animation, we can see the evolution of 400 initial conditions in the boundary of Apophis' current uncertainty box. At the beginning of the animation, we can see the 2029 close approach. After that, the uncertainty stretches along the orbit, as we've seen in the Kepler examples. But perhaps the most interesting part is that in 2043, we're going to see that another close approach significantly affects the orbital uncertainty. And we will see that in the dispersion of these blue points. Just a few seconds more. Right here. So that close approach is going to really affect Apophis dynamics. No? So we're interested in predicting both the 2029 and 2043 close approaches. The most common way to study a planetary close encounter is to project the orbital uncertainty into something called the target plane. The idea is that in this plane, the origin corresponds to Earth's center. So if any of these blue points here falls within a circle with the same radius as the Earth, that's basically a potential impact. So we want all these points outside Earth's radius. Now, in the left panel, we can see the 2029 close approach. And in this year, Apophis will approach Earth to a distance of around 6 Earth radii, which is pretty close. It's around a tenth of the distance between the Earth and the Moon. It's perhaps one of the closest approaches that we will see in upcoming years. However, despite this very close encounter, the uncertainty in the 2029 close approach, it's pretty well constrained. So we know Apophis will not collide with the Earth in 2029. However, by 2043, the uncertainty region has stretched significantly, and it's much more complicated to give a prediction regarding a possible impact. And also, this means that a single jet transport polynomial may not be enough to represent the uncertainty by 2043. And we can see that in this plot. Here we have 1,000 points that come from Apophis's current 3 sigma uncertainty ellipse. The axes represent deviations from the nominal initial condition, both in semi-major axis and eccentricity. Both axes are scaled to Apophis current uncertainty. As a reference, the current uncertainty in semi-major axis is around 450 meters. This is pretty small, but it grows over time. And the color shows the logarithm of the difference between each point and a Monte Carlo integration. Now, the left panel shows a very typical behavior of using a single polynomial. That is, it's quite precise near the center, but it gets worse as we move away from the expansion point. Instead, an ADS integration maintains a low error all throughout the uncertainty box. There's just one detail, and that's there are a few points around the -2 vertical line that have a huge error in both panels. So these are the most complicated initial conditions because of the accumulated effects of many past close approaches. So these points cannot be studied with neither a single polynomial nor with ADS. These have to be studied manually with Monte Carlo integrations. So although ADS cannot get rid of these points, it can improve the convergence over the whole uncertainty region. Now, this ADS implementation is still a work in progress. We have still a lot to do, especially to improve performance. Most of the performance in Taylor integration heavily depends on Taylor series. So previous version of Taylor series used to do a lot of intermediate allocations when operating with polynomials. So a lot of recent PRs have reduced significantly the number of allocations, but there's still a lot to do. Also, because each split is independent from each other, it would be very easy to distribute the splits over multiple cores, significantly reducing the computation time. Also, right now, we write everything to a JLD2 file, but the size of these files can grow very rapidly with the time of integration, with the number of splits, or with the jet transport order. So we have to reduce the size of the files that we write to disk. Also, depending on the application, we can save some time by stopping integrations or by dropping splits. For example, if we are studying an asteroid and one of the splits gets inside the Earth's physical radius, we can stop that integration because basically that asteroid already collided with the Earth, so we can stop that. Also, we might be interested in a particular subset of the uncertainty region, so we can drop all splits that do not cover that subset of interest. And finally, Taylor integration can be called from the SciML interface, but ADS is not available in that interface yet, so that's still pending. So that's pretty much everything. Thank you for your time.
So, yeah.
Hi. Test. Okay. Hi. Thank you for the talk. So I was a couple of minutes late, so maybe I just missed it. But about like the uncertainty propagation, have you, because when you showed like the animation, I think the first animation, it looked like polynomial zonotope. So have you considered like using polynomial zonotopes to propagate the uncertainty through the dynamical system?
This one?
Yeah, like that one. If you look at the set, it looks like a polynomial zonotope. So might be modeling that with polynomial zonotopes could help propagate the uncertainty. Have you considered that approach?
Polynomials with?
Polynomial zonotopes. Like instead of a no simple zonotope,
Uh-huh.
using a polynomial zonotope, so you have like higher terms in the zonotope, and it becomes like
Okay.
more nonlinear.
That could certainly be an option. Yeah.
Because generally it like reduces the overestimation when propagating through the dynamical system compared to zonotopes, so could help.
Nice, yeah. Are you aware of any Julia?
Yes, I brought
tool?
that.
Nice.
Yeah,
Okay, yeah, let's
so
talk
it's
then.
implemented in lazy sets. Polynomial zonotopes are implemented in lazy sets, and there's some supported reachability analysis for reachability with polynomial zonotopes.
Yeah,
So
it'd be nice to connect the tools. Yeah, nice.
Yep.
All right.
Thank you.
Yeah, just wanted to ask if I missed it, does this give like guaranteed enclosures or like So, like one of the other packages that uses Taylor integration is Taylor models.jl, which gives
Mhm.
like this interval enclosures.
Yeah.
Does this provide similar guarantees or like yeah, and also like just kind of a comparison.
Yeah, no. Up until now, we have not implemented the guarantee from Taylor models or interval arithmetics. What we do have is a tolerance error, both in the integration and also in the splitting. So yeah, that's the error that we can play with the tolerances. We set pretty low tolerances for, but yeah, that can also be an option to try to go in that direction. But then the computations also become really intensive. So yeah, there's going to be some kind of trade-off. No?
Yes, ADS is not rigorous, so we do not have.
Yeah.
Yes, so ADS, automatic domain splitting, is not rigorous, so we do not have a rigorous control of the error. And maybe in these first examples, it might be possible to use something like Taylor models, but when we're modeling something like Apophis, and we start considering long integration times and non-gravitational accelerations, etc., as Jorge said, using a rigorous integrator might become too expensive. So this is kind of a myth point.
Yeah, and yeah.
Yeah, I had two questions actually. The first was, does Taylor integration handle events so that way you could look at, say, the Taylor expansion around the uncertainty of time of closest approach?
There is some functionality to handle events, but it's probably not as okay. Then the native methods in Taylor integration are probably not as customizable as in the differential equations ecosystem. So that's why we are looking at the possibility of probably either developing our callbacks, right, and at the same time being able to use the SciML interface, right? We have an interface to SciML currently, but yeah, in order to use all the callback libraries, options, and everything, yeah, it'd be nice. Yeah.
Gotcha. And then my second question was, could you just quickly describe the difference, I guess, between using something like Taylor diff and a differential equation and the Taylor integration?
Taylor diff?
Yeah, Taylor diff.
The
AD package that does, Taylor approximations around.
Yeah, we have not used Taylor diff here, but that could be another option to explore, right? Okay. In order to also improve the performance, that could also be certainly an option.
Thank you.
Oh, thanks.
Is this a question? Yeah. Okay.
Those are very cool plots. I like the animations. I was wondering whether, do you just do the computations on the boundaries to show the trajectory, and you make an assumption that everything inside the boundary stays in the boundary, or does some things break down when, like for example, you add too many bodies and it becomes a bit chaotic?
No, it's okay. It's okay. It's okay.
Yeah, so in these first examples, the Monte Carlo panel basically means put a lot of initial conditions in the boundary of the box and propagate them, and assume that it's gonna remain convex. And in this example, it works. But if you try to do that in this one, that's not gonna remain convex. So it depends on the application.
Okay, let's. Oh, do you have a question? Yeah. Let's thank the speaker.